Nice. So now you signed your consent.
Yeah.
Wait, so the people online don't know when the test is?
Exactly.
Next Thursday!
Hello and welcome back to Calculus 3. Settle down, savages. We are supposed to talk about the shell method. Apparently something is happening next Thursday. So I'm not sure if people want to stay away from... But anyway.
Oh, man.
You know, quiz 7 is on the test day anyway. So, shell method, right? Welcome to Calc 2. Did I say that already?
Yeah.
Whatever, just start from scratch.
Welcome to Out 2.
Hello and welcome back to Calculus 2 section 6.4 shell method. We are still going to rotate functions around x or y axis and compute the volume of the object that we get. Now these objects, since we are rotating around the axis, will still have circular base, right? So we are still talking about cylinders, bottles, cups, and all of the things that would have rounded base. Now the difference between the disk method and the shell method is going to be the way we cut. So to review what we had yesterday, we get a little disk, right? That disk has the delta x thickness on it.
It's not supposed to be on the board.
You're not writing.
Yeah, it's just a lag, so it eventually will come up.
Oh, this bandwidth.
So the disk, yeah, it's too hot.
Hey.
So we have a little disk in this case as we cut, and we see that as we cut this way, the cut is always perpendicular to the axis of rotation. Now today we can take the same object, which is this cylinder, rotating around the x-axis, but we can actually cut that with dy. Now, if I cut this object with dy, right, that will create the cut, it is going to create shells. So now you are creating rectangle-like shapes, which are, well, they don't have to be rectangle, could be trapezoids and all of these other kind of things. But the important part is that these shapes would be delta y thin, and you will stack those up to get the formula. So one of the first things to learn regarding shell method is the fact that if you're rotating on x-axis, you are setting up a dy integral. Where for the disk method, if you are cutting dx, you are setting up, if you're rotating around x, you are setting up a dx. So they match for disk and they're opposite for shell. Now let's talk about this shell method. What I have is a method that cuts parallel to axis of rotation. So cuts are parallel to the axis of rotation. And we have the volume formula, which states 2 pi integral c to d. And I'm going to change this formula slightly than what's in the book. I will say that this is going to be p of x, h of x, sorry, p of y, h of y, dy, if we are rotating around x-axis. If we are rotating around x-axis, y-axis, we have 2 pi a to b, p of x, h of x, dx, and that would be the y rotation. So these are the formulas. We are expecting these formulas to be third-dimensional, and they are. because you have 1, 2, 3 dimensions inside the integral, right? You have a function p, function h, and the dy. Now, the book has the simplest possible formula only, but that formula, unfortunately, will not cover every situation you might run into as you move along. So the book gives you the formula that the volume is equal to the integral a to b of 2 pi x f of x dx, right? And technically, in my formula that I gave, this over here is the p of x, but as you can see, in my case, you can actually put something else there rather than just x. And then f of x is the same as h of x, but I'm using h to represent the height. So I actually have to show this on a diagram to actually make sense, but the formulas, the way I have it, you read them integral of position times the height times dx or times dy. So position times height. That's why we are using p and h. That's what they stand for. Now let's see, as you are setting up these integrals, what do these things actually mean? So say you have an integral that is going to rotate on x-axis, and let me draw the shape. So say you have this situation. I'd say this is what you have, and you are rotating this around the x-axis. Now, can you use disk or washer method? And the answer is yes. However, you have to use two integrals, because delta x over here is going to touch the function on top and this one on the bottom, which is x-axis. And when it's on this part, it's going to remain at the top function, I believe that's 2. And then the bottom function now switches to this, whatever this function f is. So because delta x is operating between different functions, you have to set up a separate integral for each case where delta x is following different. And in this case, on the bottom, right, that's exactly what's happening. So maybe we can do better. And this is what the shell method is for. Because if I am able to set up a dy integral over here, then as you can see, as this dy slides from 0 to 2, right, it always has the left-hand side sliding on y-axis and the right-hand side sliding the function. So I would like to set up the integral, and this is where the shell method kicks in. So in this case, it's not the other method is impossible. This case, this method is just more convenient, right? You can still do the problem using disk, but so what is this formula over here? That's 2, so that's x minus 2 as the square root, right? So the function is equal square root of x minus 2. Clearly this is 2 as a function. We have 2 and we have 0 over here. So now if I want to set this up, volume as we rotate around x-axis. So if I'm rotating around x and I'm using shell, we are using 2 pi, we are using y limits. So that would be 0 to 2. It will be 0 to 2 because the lowest dy can be is at 0 and the highest it can be is at 2. Position function is just y because this representative rectangle dy will swipe all of the y's between 0 and 2. And the height, and in this case actually the length of the formula is, well, you can't put square root of x minus 2. You can't put the square root of x minus 2 because your formula has to be given in terms of y. So you have to massage this, right? y equals square root of x minus 2, y squared is equal to x minus 2, x is equal y squared plus 2, and that is what goes in here. And finally dy. So we are able to set up one integral, and also because we had to convert the function, right, to express x from the function, we had the we also got rid of the square root, so now it's even easier to integrate and do everything else. So now what I have is 2 pi 0 to 2, and I need to integrate y cubed plus 2y dy. Now that's 2 pi. We have y to the 4th over 4 plus y squared, computed from 0 to 2. So 2 pi, open parenthesis, 2 to the 4th 16, it's a 4 plus 4, minus 0, no one cares, so that's going to be 816 pi. Units cubed. So we have a volume of 16 units cubed. Yes?
Why is y the position of it?
The position is which way. So if I can draw these on the picture. Here is your p of y, and here is your age of y. So you can see that p of y is swiping all of these values between 0 and 2. What the formula allows you to do is to have axis of rotation away from x and y axis. So I can actually have this problem. If I have the same, I will erase this, but so I have the same thing over here, same shape, but now I say, you know what, I want to rotate this around this line here, not around the x-axis, but I want to rotate here, right? In that case, the position for this one, right, your position of y is now going to be 2 minus y. All right? So it should come back because this blinked. So let's see. It hopefully picks up. It's back? Good. Yeah, the bandwidth today is tricky. I think our Calculus was the same time, few times blinked, so hopefully it's one piece. We're done. Yes. Oh no, we have. I will do more problems, but yeah, don't panic.
P is the axis of rotation, and then the height is equivalent to the other.
It's just like the area between two curves, right? So that's
Okay.
your f of x.
So just the so f of x.
So we'll do some of those objects that have. What do you have?
Can you scroll back up a little bit?
A little bit, sure.
No, like to the point.
Oh, more. Okay.
This definition.
Oh, definitions. There. Oh, you said a little bit at first, so all you get is a quarter of an inch. All right. Now, again, the shell method can have two functions, right, that work together. So now we are going to extend this formula because I could have situation where I have, let's say a linear line over here, and then I have a parabola here, and now that rotates on x-axis, right? So we only worry about this piece here, and as you rotate that part, it will create similar on the other side, and it will give it a round shape. So it will look like a cone from the inside, but it will have this kind of heart-like, right? This part here looks like a heart. and that would be round. Now, since you are rotating on x-axis, and we have these two functions, this is the case where you hopefully see that the disk method cannot be done, because I am not able to have delta x right there, because it folds on itself, right? The function folds on itself. So I must have dy. So this would be one of those cases where you have to use the shell method. And if you draw representative rectangle dy, right, you see that you have the function that is further away, we like to call that f, and the function that is closer by to the y-axis, and we like to call that g. So now, to set up this particular integral, we would just say volume is equal to 2 pi integral c to d, because we are doing dy, and now you're going to have f of y, p of y. In our case, if you're rotating on the axis, then that's just y. That's that. If you're rotating away from the axis, then, so you have p of y, and then over here you have f minus g. So f of y minus g of y, everything dy, and that's the x rotation. So this would be the most general. This is like, the washer method is the most general method, and the disk method is a special case when the bottom function is the x-axis or the y-axis. Well, in this case, right, you have two functions. So please keep in mind the progression in mathematics at all times, right? You learned that there is a single integral to calculate area under the curve. So you had the integral of f of x, right, which was the area under the curve, and this was actually f of x minus 0, because the bottom is the function y equals 0, which is x-axis. But then we upgraded that into f minus g for area between two curves. Then we said, let's rotate and have pi integral of f squared dx. And then we said, but wait, what if we have two functions? Well, that was pi integral f squared minus g squared dx. So you always have the simple case where x is the bottom, and then you say, well, what if I have actually two functions and I don't have the flat bottom? So now you have a rotation, and then again two function rotation, and then you have a shell, right, with p, and then you just have py hy dy, right, for the basic case when the bottom is flat, but then you have 2 pi p of y, and then we just say f minus g dy, which is the most general case. So this f minus g, as you can see, it's present in every single one, right? As soon as you have two functions, that traps the area, guys, and it's the area that it traps that rotates and creates the shape. Now, if I don't have the second function, if I don't have g, then the entire bulge over here is the one that it's going to rotate, right? And it's going to create the shape that it's like those pies that have a hole inside, whatever they're called. You know, the cakes or what, I don't know what they're called.
The bundt cake?
I'm sorry?
A bundt cake where it has a little hole?
Yes.
Yeah.
So that's that would be the shape, right? If this line wasn't there and you had to rotate the entire piece around, right, well, you kind of separate it a little bit to have a hole, because this would not have a hole. It would just all kind of point into a single point here, right? But yeah, that's the case.
On that, you wrote f of y minus g of x.
It was supposed to be a y there. Oh no, it is y.
That's horrendous.
No, it is y. It's y. Look,
Now.
that's clearly a y. Please pay attention, okay?
I would have been offended, but I don't want to give you no money.
There we go. Problem solved. Yes.
So the second term is just the area, no matter how you're defining it?
Yes.
Okay. The first term is the axis of rotation, and the area, and then the differential.
And yes, differential to give it a thickness, and this smooths it out. Yes, a lot of people don't get those kind of references. If you have a rectangle, I'll erase this again. Area is A times B, because you have A and you have B. If you have an ellipse, which goes in here or goes around, right? Which is the area for that is AB pi. What does it do? It just makes a round. And now if you have a square, which is AA, your area is A squared. If you have a circle with a radius R, it's R squared, and there's your rounding constant, right? So the same thing up there. You know it's round because there's pi in formula. You still have the rotation. Yes?
So for the ellipse, would you be using the vertex or the foci?
For what?
For the AB times pi.
The AB, those are the minor and the major radii. Okay. So that's the half of the length is A, and the half of the entire height, half of the height is B.
Okay.
Okay. So now that we took care of this, let's hunt for some of the problems in the textbook. For homework, the lecture is technically over. That's they do have, I think they have a summary. I did not mention Larson's calculus textbook, guys. If you are looking, right, if the book is not making you happy for whatever reason, and you're looking for the book that students claim is the easiest to understand for calculus, just go online and find like $10-15 Larson calculus. You can probably go with the like 7th edition or something. It's dark blue. Let me see.
Actually, the calculus is done with it's yellow.
Let me see if. So you should be able to find this like on Amazon. Yeah, there it is. You find this on Amazon or whatever. The way he explains these things is just like a joke. So it goes, this book is, as you can see, the current edition of the book, the previous edition of the book. This is a 12th edition, that's the 11th edition, that's the 7th edition, that it's like more than 10 years old. All they do is they just change pictures, add more problems, and shovel the pages around. So, it... This price, no, this is way too much. Students are finding this for $13-15 every single semester. So you can find, and I'm talking Calc 1, 2, 3 hardcover. I'm not talking 7 pages of the book. It's the full book. You can find it, and it is very, very easy to understand. Now, the graphic that I'm going to show you from your book is much better in the Larson book. But these pictures here show the difference between disk and shell method and when you are supposed to use each of these methods. And as I mentioned, some problems, both methods are possible. Some problems, one method is more convenient than the other, and for some problems, only one method is possible and the other one is not possible at all. So you have three different flavors of these problems. And then, again, experience, amount of homework, and interest, and all that stuff will determine how well you're understanding and doing. Now, I want to see if we can come up with some. There they are. So these are all examples in the textbook. So if you look at the problem number 6, that is the one in the middle over here, right? Problem number 6. You see immediately that the disk method cannot be used, because disk method would require you to cut with the dy integral because it's a y rotation, and if you put dy rectangle in the top half, then function folds on itself and integral is 0, so garbage, right? So you are forced to use dx So problem number 6, this problem as well, right? Because you're rotating on y, you can't put dy because it touches the same function, right?
Right.
Top and the bottom. So you would go this minus itself, and when you integrate 0, what do you get, right? So you have to go with dx. So axis of rotation parallel to the cut, which is dx. So y rotation dx, that's a shell method, right? But then you go to this problem here, the problem 15. Problem 15, choose whatever L you want. Doesn't matter, right? Because you can use shell method, right? Because the shell method is going to be parallel. You go between these 2 points. Or if you use the disk method, which is going to be faster for this problem, you just go this way. So let's do problem 15 both ways. How about that? And then we're going to go back to problem 6 and solve it with the only method that is available to us. So problem number 15. Problem number 15 has a square root function. And the only thing that, well, not the only thing, things that you cannot change about the problem is the rotation, right? Because rotation would actually change what the object looks like, the end product. And you are not changing the functions because that would also change what the problem looks like. So now, if I am rotating this piece around x-axis, we see that we can actually draw both dx and dy. Yes?
Oh, we can't see it.
Oh. So.
Welcome to out too.
What happened? There you go. So now we see that we can put both. We can do dx, we can do dy. So I'm going to start with the disk method first, which requires dx, because I need the cut to be perpendicular to the axis of rotation. Well, when I set the volume integral here for the dx representative rectangle, I have pi integral 0 to 4, and then we have our function squared, well, that's square root of x squared dx. Whoa, that's really cool, right? 0 to pi, we are integrating x dx, so this is really easy. 0 to 4. So we have x squared over 2, 0 to 4. That's a 16 divided by 2, it's 8 pi. So the volume of the object up there is 8 pi. Now let's do the shell for the same problem because we can. And shell will work with the dy because the cut needs to be parallel with the axis of rotation. Now we are rotating around x, so our position function is just going to be y. And I now need to figure out what this y over here is. So we'll figure it out when we compute square root of 4, which is 2. So volume is 2 pi integral 0 to 2 y times, and now the height. Well, that goes as 4 minus y squared, and then dy. Now you go y 4 minus y squared. Well, observe that the top is always on the function x equals 4. So this function over here is x equals 4. Remember that we have to plug in x equals function of y in these equations. This function, so this over here is x equals 4 function. Now this function over here is y equals square root of x, but then when you fix that into x equals, you get y squared. So we are using that x equals y squared. we are using the formula f minus g, because we have function that is far apart, further away, minus the function close by. Right? We are using the general case with two functions. So now when we compute this, we better get 8 pi. So we start with a copy 2 pi, integral 0 to 2. What I need to integrate is 4y minus y cubed dy. That is 2 pi. Integrate this, we get 2y squared minus y to the 4 over 4 from 0 to 2. That's going to be 2 pi. Integral, it's 4, that's 8, minus 2 to the 4th is 16, divided by 4 is 4. And I have zeros just dies. I have 2 times, so that's 4 times 2 pi, 8 pi. There we go. It's the same answer. It has to be the same answer because we just used a different method to solve the same situation. That's the beauty of math. All of the answers have to match. And we see that this problem was possible. Now, again, as you practice this and as you learn, you see that one method is more convenient than the other. Now we're going to take a look at problem number 6, and in that problem, this method will not be possible at all. So in problem number 6, we have these two parabolas that are intersecting. So we have this parabola here and this parabola here. So these two parabolas are creating the intersection, and the rotation thing that we cannot change is on y-axis. We have the top parabola, right, to be the one with the negative x squared because it opens down, so that should be common sense at this point in the class. And so they just give you two functions next to each other, but one has negative x squared, the other one has positive x squared. You are supposed to know that the positive x squared opens up and the negative x squared opens down. You're sitting in Calc 2 class. So we have negative x squared plus 4x plus 2. And the bottom one is x squared minus 6x plus 10. So we have these two functions. Now, you first do the analysis on can I use any of the methods? And if I can use both, is one easier than the other? Well, you can immediately see that you cannot use dy because the function, right, the dy kind of folds on itself, right? The one part and the other part are both hitting the same function. So dy is out. If dy is out and there is a rotation on y, well, that means that the disk method is out. You can't use it just because you cannot set up the integral. So now, if you know that the disk method is out, by process of elimination, right, you have delta x. And delta x is the one that we actually can use. Now, delta x is okay, but there is also rotation on y. Those two things spell shell method. Because the shell method has this and this variable not matching, right? So the cut is parallel to the axis of rotation, therefore shell method. Now, I see that I need the limits of integration. The limits of integration are given in a book, but I want to one more time stress that if the limits are not given to you and the functions intersect, set the two equations equal to each other and solve. Values that you get will be the limits of integration because those will be these numbers here that bound left and right. So we have x squared minus 6x plus 10 equal to negative x squared plus 4x plus 2. Move everything to the left. We get 2x squared minus 10x plus 8 equal to 0. Divide the entire equation by 2 because we can, and we get x squared minus 5x plus 4 equal to 0. Well, this factors over x minus 4 and x minus 1. So x is 1 and x is 4. And those were the values that we were looking, because those are the values for our integral. So now I'm going to set up the volume formula using shell. I have 2 pi, integral from 1 to 4. Position. We are integrating around y-axis, so it's just going to be x. And we have the top function minus bottom function, so that's going to be negative x squared plus 4x plus 2 minus the function on the bottom, which is x squared minus 6x plus 10, and all of that dx. 2 pi integral 1 to 4 x times, and now we have negative 2x squared plus 10x, and 2 minus 10 minus 8 dx, and now you distribute dx in front, and then you can finally integrate. So we have integral 1 to 4. What we have is negative 2x cubed plus 10x squared minus 8x dx, and we can finally now do the work. So 2 pi, we don't need integral anymore. That's x to the 4th over 4, so it's negative x to the 4 over 2, because the 2 will cancel, plus 10/3 x cubed minus 4x squared from 1 to 4. And that's going to be equal to some number. Exactly. Yeah, you should be able to deal with the arithmetic once you get home and get nostalgic that the class was over, so you just want to continue, right?
Could you scroll back up like one thing?
What happened?
Could you scroll back up to the graph?
Yeah. Stop minus bottom, right? So the negative minus the positive. And that's that. That's the shell method. So just do, 15 examples, you'll be fine.